We learned the 6 quantum mechanical postulates in another video. Today we will use these postulates to solve the Schrodinger equation for a free one-dimensional particle. The time-dependent Schrodinger equation says h psi equals IH bar times the first derivative of psi with respect to time. And this h is the Hamiltonian, the sum of the kinetic energy operator and potential energy operator. R is the position of the particle in a one-dimensional universe. R is simply denoted by x, the position of the particle in the x direction. And t is time. The potential energy of a free particle is 0, or this can be chosen to be the 0 reference. And therefore, we have only the kinetic energy operator right here being applied to the wave function, which is equal to IH bar times, again, the first derivative of psi with respect to time. For simplicity, we separate time and space by expressing the wave function of the particle as a product of a function of x only and another function of t only. And then we can write out the time-dependent equation this way by replacing the psi of x and t to be with this product of psi of x and f of t on both sides. Because this function of time is independent of position, and this psi of position is independent of time, we can actually pull out this f of time out of the second derivative with respect to position. And we can pull this psi of position out of this first derivative with respect to time. And then we divide both sides of this equation by psi of x times f of t. We get a new equation here. And in the left-hand side of the equation, we see only one variable x. On the right-hand side of the equation, we also see only one variable t. How can a function of x be equal to a function of t? There's only one possible explanation. That is, both sides are equal to a constant. And this constant is denoted by E. And later you will see E is the total energy of the particle. So now we have two functions. We have this side, the second derivative of psi, divided by psi times negative h bar squared over 2m equals E. And also we have this expression is equal to E. And we'll look at this time-independent function of the lowercase psi of x first. So how do we solve this? There are two specific solutions to this differential equation. If we set this 2me over h bar squared to be k squared, then k is equal to the square root of 2me divided by h bar. If we do that, we have a simple differential equation. The second derivative of psi is equal to negative k squared times psi. The solutions are e to the power of plus ikx and e to the power of negative ikx. Again, k is the square root of 2me over h bar, or the square root of this whole thing. And then we can simply prove that these two specific solutions are legitimate. The proofs are here. So we take the first derivative of this psi plus, which is e to the power of plus ikx. We have this plus ikx appear twice in front of this exponential function. The result is plus ikx times plus ikx, which is negative k squared times the original wave function. Similarly, we can prove this e to the power of negative ikx is also a legitimate solution of the differential equation. What is the general equation or general solution for this time-independent Schrodinger equation for this 1D free particle? It is the linear combination of this psi plus and psi minus. So basically we have a linear combination here. A plus is a constant, a minus is a constant. A plus and a minus can be any constants as long as they ensure the normalization of this wave function of the free particle. What does this normalization mean? It means the integral of this psi x squared, the squared modulus of this psi x, is equal to 100%. And the physical meaning is very simple. The probability of finding this particle with this wave function from negative infinity to positive infinity, that's the entire space of the one-dimensional universe, is exactly 100%. And remember, if we plug in this general solution here, a plus times e to the power of positive ikx plus a minus times e to the power of negative ikx, in this differential equation, we can easily prove that this is a legitimate solution as well. And again, a plus and a minus can be any constants as long as this overall general solution is normalized. Now, what's the physical meaning of k? Remember, k is equal to the square root of 2me over h bar, and remember, for this particular problem, we have potential energy equals 0, and then E equals simply the kinetic energy, and the kinetic energy is half mv squared. And then we reorganize this, we get m squared v squared. And then we take the square root of that, we have the absolute value of mv, that's the absolute value of the momentum of the particle p. Therefore, p is equal to kh bar. And then we know that k is simply the magnitude of the momentum of this particle in terms of h bar. What is h bar? In the SI units, h bar is the so-called reduced Planck constant. It's equal to h over 2 pi, which is 6.626 times 10 to the power of negative 34 joule second divided by 2 pi. So it's roughly 10 to the power of negative 34 joule times second. In quantum mechanics, there's so-called atomic units. The four fundamental atomic units are the charge of electron is 1 atomic unit, the mass of the electron is 1 atomic unit, and also the value of h bar is 1 atomic unit, and 1 over 4 pi epsilon, the electric constant, is 1 atomic unit. To avoid ambiguity, we should say the absolute value of the charge of electron is 1 atomic unit. And the physical meaning of this wave function of the one-dimensional particle is very simple. This particle is moving in the positive and negative directions at the same time. And if we measure the momentum of the particle, we may get kh bar or minus kh bar. The ratio between the probabilities of seeing the particle moving forward versus backward is a ratio here, a plus squared versus a minus squared. The differential equation of time is the first derivative of this f function of time with respect to time is equal to e divided by ih bar times the function of time. This results in this function of time is equal to an exponential function et over ih bar. You can verify this by plugging this ft in here and in here. You will see this equation holds. Therefore, the time-dependent wave function of this free one-dimensional particle is this. The total wave function here, which is time-dependent, this is equal to the product of the time-independent function of x times the function of time. And over here, this time-independent wave function is of the most importance in undergraduate physical chemistry. So we're focused on this one. But also here it gives you the function of time. It's an exponential function of the energy multiplied by time divided by ih bar. It also tells you in future that there's a second form of the Heisenberg uncertainty principle, which is the uncertainty of energy times the uncertainty of time is greater than 1/2 of h bar.